Dear students, welcome to probability distributions. In the earlier video, we have discussed about random variables, the types of random probability distribution such as discrete as well as continuous. We had quite a handful number of problems in these particular random variables. Hope you are all following them. In continuation to that, now let us look at probability distributions, which again is based on these random variables which I have seen earlier. And here also we have two kinds of probability distribution, namely discrete probability distribution and continuous probability distribution. So as we know, the behavior of random variables is well described using probability distributions. So probability distribution can be either discrete or continuous. Now when you look at discrete probability distributions, we have a binomial distribution. We also have Poisson distribution. So binomial distribution you might have heard, Poisson distribution as well. These two come under the category called as discrete probability distributions. At the same time, we have exponential distribution, normal distribution. These two come under the category of continuous probability distribution. There are other distributions as well, but these four are predominantly used in the statistical analysis. So binomial, Poisson comes under discrete probability distribution, while exponential, normal distributions come under continuous probability distributions. Now let us see the discrete probability distributions, that is binomial and Poisson. To start with, let us consider binomial distribution. So binomial distribution, as the name says, we are talking about it as a binomial. We know binomial theorem, we know binomial coefficient. Bi stands here for 2. So that means whenever there is or whenever there exist two kinds of possibilities, for example a success or a failure, acceptance, rejection, occurrence, non-occurrence, yes, no, dead, alive, like that, when you have only exactly two kinds of outcomes possible out of a trial, then we say binomial distribution is the one which can be used for such kind of probability. There will be only two outcomes possible, either true or false, either failure or success, either defect or not defect. Like that, we will be having only two outcomes out of a given trial. Or when you put a toss a coin into toss, you will get either head or tail. There is no third outcome possible in this case. Like that, we have a success, a failure, a tail or head. Only two outcomes. Let it be any outcome, but only possibility for two outcomes. If that is the case, probably we can look into binomial distribution. Now binomial distribution mathematically follows a Bernoulli trial. Don't worry about what Bernoulli is. They're all based on the mathematical terms, where the experiment consists of repeated trials, and each trial comes with a outcome either true or false, or success or failure, and the probability of these trials remains constant since they are all independent. Each trial in our Bernoulli process or binomial are going to be independent. We have a constant probability since they can happen at any point of time, irrespective of the time when how they are going to happen, their probability remains same. These are the various conditions under which binomial theorem is applied. But for us, we should keep these two in mind. The events are very independent, meaning that they will not depend on the probability of other event. At any point of time, each event will be resulting either in success or failure. Like that, only two outcomes. That's why it is a binomial. Okay. So binomial distribution we apply when these conditions are occurring as far as the probability is concerned. And if you look at the application areas of binomial distribution, we can use them. Probably depends on the problems which contain identifying the number of defectives out of a manufacturing sample or assembly, estimating the reliability of systems, estimating whether what to say, the health rate of a system or society, number of rounds fired from a gun hitting a target. Like there are various applications like military applications, healthcare systems, manufacturing industry. These are the places where binomial distribution can be used. But irrespective of the system where it is going to be applied, the outcome remains same. What is the outcome? Wherever there are only two possibilities, only in those situations binomial distribution can be well suited or well used. That we should not forget. Now, so coming to our discussion today, in binomial distribution, what are all the formula that we can use? So assume n is the number of independent trials, because independent you need not say, because binomial by default is a independent, and p is the probability that the success happens in the given trial. Please remember this word. We are going to consider P as the success. When you take P as the success, see every trial has a success and failure. That's what the binomial is. When I say P is the success, obviously complement of P, that is 1 minus P, is going to be failure. That we should remember. That is how probably we are going to use now. So for every event to happen, there will be success. At the same time, there will be failure probability. But we are considering P as a success. At the same time, we consider Q as a failure. Q here can be a complement of success, that is 1 minus P. So if that is the case, the mean of this binomial is going to be n into P. Mean is represented as mu here. So mu is equal to n into P. N means the number of trials, P in probability of success. Similarly, variance sigma square is nothing but n number of trials, P probability of success, Q probability of failure, which is nothing but 1 minus P. Sometimes you will see this as n P into 1 minus P. Why 1 minus P? Because Q is nothing but 1 minus P. So here to understand, the variance is going to be n into P into Q. P is a success, Q is a failure. Once we know the variance, we can easily calculate the standard deviation, which is nothing but square root of variance, that is nothing but root of NPQ. So the probability mass function, since we are talking about a discrete probability distribution, all discrete functions will have mass function. That's what you have seen in earlier video. So PMF for binomial distribution is given as NCX, which is a combination formula, then into success is P. So P power X, Q is a failure, Q power N minus X. If you look at X is nothing but the number of times the positive thing is going to happen or the probability or success is going to happen. So N minus X is nothing but out of total some are success, remaining will be failure, that is nothing but N minus X. And we also know that Q is nothing but the probability of a failure. So with all probability, NCX is nothing but out of n options, what is the number of occurrence of a success into probability of success over number of successful items into probability of failure, that is Q, above power of n minus x, that is again the number of failures. That is how the formula has been given, simple formula. So B of x is equal to NCX into P power x into Q power n minus x. So Q is a failure, n minus x is also failure, while P is a success, x is also success. The number of combinations we are going to identify from this. That's what we are going to see now. Okay. Now let us take with this introduction some of the problems that deal with the binomial distribution. So last time couple of examinations we had this binomial problem being asked to 6 to 7 marks. So please understand the question as usual. What to do with the probability you should be able to figure out. The first question is the probability that a pen manufactured by a company will be defective with 1 by 10. If 12 pens are manufactured, find the probability that exactly 2 pens will be defective, at least 2 pens will be defective, none of the pens will be defective. So here they are not given whether it is a binomial, a Poisson, normal, exponential, none of them have been mentioned. So how do you figure out it is a binomial distribution? So just now we have seen wherever there are 2 outcomes. So here a pen is manufactured, it can be defective or not defective. Only two outcomes. So we can attribute this as a binomial distribution. At the same time, the number of manufacturing is also very less. The less number of items, 12 items, 13 items, 10 items, that is also, n is also very small. So two things what you have to observe in binomial is the number of items involved in the distribution also will be less. If you go to Poisson, the next case, that is infinity, there we have a more items or a large number of items. But in the case of binomial, the number of items, the n value is also very, very limited, because discrete we know itself is a countable set which is going to be finite, and in the binomial especially it is going to be very, very less size also. So that also will let us know whether it is a binomial distribution. And so two things here. So we have two, either a pen can be defective, non-defective, like a failure or a success, like a acceptance or rejectance. We have only two outcomes, so binomial is best suited. Second, the n size n here is 12, only 12 pens we have, so that is also very less. So both will tell us to go for a binomial distribution. Now having identified it is a binomial distribution, let us figure out n and p. So n is 12, so p is nothing but probability of a pen being defective. So you can define a failure as a p or a success as a p. So that depends how you take. In this case we are taking defective as a probability p, then non-defective will become q, that is complement of it. So 1 by 10 is 0.1. A pen is being non-defective is 1 minus 0.1, that is 1 minus p, that is nothing but 0.9, which is nothing but q for us. Okay. Now first one, exactly 2 pens will be defective, exactly 2, that is x is equal to 2. So what is the probability that we have 2 pens exactly are becoming defective? That is b of x. So b of x, NCX, what is n? N is 12, x is 2, x is equal to 2. Here it can be taken as x is equal to 2, exactly 2. That is why it is equal to 2. So then p is nothing but 0.1 power x is 2, remaining is q is 0.9 power n minus x, n is 12 minus 2, 10. So this is what we are applying in this. Straight away if you apply, you will get 0.2301. Probably you might have gone through the video that I have shared how to calculate the NCR and stuff. That will help you to calculate how to quickly what is the value of NCR. So using that you will get 0.2301, that is exactly 2 pens being the defective. So next one is at least 2 pens, at least. So x is greater than or equal to 2, at least, only 2 minimum. It can be more than 2, but at least 2 pens being defective. So at least 2 can be calculated as 1 minus b of x greater than or equal to 2 can be written as 1 minus b of 1 or 1 minus b of 0. So 0, 1. If you remove them, whatever you get is nothing but more than 1, that is equal to 2 or more. So that's what we are going to get. So 1 minus, this is b of 0, this is b of 1. So b of 1 is based on again 12cx, 12c1, then 0.1 power 1, 0.9 power 12 minus 1, because x is 1. In this case x is 0, so x is 0, 12c0, p power 0, q power 12 minus 0, that is 12. So again if you substitute, you will get 0.659, that if you subtract from 1, you will get the actual probability. So what was required here is at least 2. At least 2 means minimum 2, and it can be more than 2. That's why we have written it as a x greater than or equal to 2. So if at all we have to calculate strictly speaking b of 2, b of 3, b of 4, b of 5, b of 6, b of 7, b of 8, b of 9, b of 10, b of 11, b of 12, which is going to be very, very complicated. Instead of that, what you can do, 0 and 1 if you calculate, subtract from 1, because we know the total probability will be 1, we can get this. So it's just a logical way of applying this formula. Okay. So that's what we get, 0.341. Now let us see the third one, probability that none will be defective. That means no one, all 12 are going to be perfect. If that is the case, x is going to be 0. When x is equal to be 0, that is NCX, NCX, x, 12c0, p power 0, q power n minus x, that is 12. So we'll get exactly 0.2824. So that's what is being asked, and we have could able to calculate. So this is a binomial distribution. Now let us take another problem. In a sampling, a large number of parts manufactured by a machine, the mean number of defective in a sample of 20 is 2. So sample is 20, that's why n is very small. So mean is 2. Out of 1000 such samples, how many would be expected to contain at least 3 defective parts? So we have found that in a sample of 20, the mean is 2. What do you mean by mean? You are getting mean number of defective. That means when you take 20, you will get 2 at least. That is only mean. It might be more than 2, 3, 4, but mean is 2. So if we have 1000 such samples, how many will be having at least 3 defective parts? Okay. So this is also a binomial distribution problem because sample is very less, and we have again defective, non-defective, only 2 outcomes. Thereby we can consider binomial distribution. So here n is equal to 20, small sample, mean is given 2, mean is nothing but n into p. So we know that np is equal to 2. We know n, we can easily calculate what is p. So p is nothing but 0.1. So what is the probability of defective? Why you are taking it as a probability of defective now? So we have given that the number of defective in a sample whose mean is 2. When mean is 2, that corresponds to defective, so your p also should be corresponds to the defective item. Thereby the probability of defective is nothing but p. So q, which is the probability of non-defective, is calculated as 1 minus p, that you will be getting as a value which is nothing but 0.9. So that value is 1 minus 0.1, that is 0.9. Now what is being asked now? What is the probability that 3 will be defective? At least 3 will be defective. That is probability of at least 3 defectives in a sample of 20. So what are the 2 ways we can calculate this now? Probability of 3 plus probability of 4, probability of 5, 6, 7, 8, up to 20. 17 calculations we have to do. Instead of that, what we can do? We can take the other way. That is the probability of 0, probability of 1, probability of 2, only 3. Addition, add them, subtract from 1, you will get the result. So whichever is convenient for us, you should be able to do now. So I think this is convenient for us, that is taking probability of 0, probability of 1, probability of 2, that is b of 0, b of 1 and b of 2. Probably if you add them, you will get some number, subtract that number from 1, you will get the actual probability. So b of 0 is nothing but nc0, p power 0, q power n minus x, that is n, plus nc1, p power 1, q power 20 minus 1, that is 19. Again nc2, that is 20c2, p power 2, q power 20 minus 2, 18. So substitute that, you will get this value. So final value is 0.3227, which is the probability that at least 3 defectives will be there in a sample of 20. But our question is not ending there. What are they asking? There are 1000 such samples. That means we have taken a set of sample 20. Now 20 sample size we have 1000. That means total we have 20,000 items being checked. So each 1000 sample size, which is 20 each, how many will be there? So now we have to multiply that. This sample what you have calculated is only for a one sample. So for 1000 samples, multiply by 0.3227, that is equal to 323. So that is the final value. So, next problem. Probability that a patient recovers from COVID-19 is 0.4. If 15 patients are known to have contracted the disease, what is the probability that at least 3 patients survive, exactly 5 patients survive, none of them survive? Again we have to figure out whether it is a binomial or not. So for binomial, event should be independent, So each patient is separate, independent. There are only two outcomes, either survival or not survival, only two outcomes, and sample size is also less, 3, that is 15. So thereby we can say this can be considered as a binomial distribution. So given that n is equal to 15, you can write every time the given distribution is binomial, because that gives clarity for both you and the examiner. Now the probability, the n is given 15, the probability that a patient survive is 0.4, that is p. The probability that patient do not survive is 1 minus p, that is q, 0.6. Now what we have to calculate? At least 3 patients survive, at least minimum. So probability that at least 3 patients survive, minimum 3, it can be more than 3. So that's why it is bx greater than or equal to 3. So 1 minus p of 0, p of 1, p of 2. I am also using b0, b1, b2, all are fine. Whichever is convenient for you can use. You can use b0 plus b1 plus b2 also, nothing wrong, as long as you can understand. So now b of 0 is ncx, p power x, q power n minus x. Same formula we have used for b of 0, b of 1 and b of 2. If you calculate, you will get 0.0272, and 1 minus that value will give us 0.9728, meaning that probability that at least 3 patients out of 15 survive is very high, that is 0.9728. Next is probability that exactly 5 patients survive. Exactly 5. Exactly 5 means x is equal to 5. So 15c5 x power, sorry, p power x, q power n minus x, exactly 5. So we'll get this formula. So direct substitution, it is very less, 0.1857. Next, probability that none of them survive. None means x is equal to 0. So x is equal to 0. So this is very, very less. None of them survive is 0. That means most of them will be survive. None of them survive is very, very less, 0.004. So it means the opposite of that, everybody will survive. That is very, very high. So this is what we can make out. So based on this, probably you will be able to understand how binomial distribution can be applied. So let us have look at another problem. Let x be a binomial distribution. See, in this problem they have given, so binomially distributed random variable with mean 2 and standard deviation, find the corresponding PMF. This is a different kind of problem. So based on the formula, so it is given that we have a binomial distribution. In binomial distribution, mu they have given, standard deviation they have given. So we know the formula. In binomial distribution, mu, that is mean, is nothing but n into p, that is given as 2, and they are also given the probability. Sorry, they are not given probability. Now they have given what? Standard deviation. Standard deviation is nothing but square root of variance. We know what is variance. Variance is nothing but sigma square. What is sigma square? NPQ. So NPQ is 2 by root 3 whole square. They have given standard deviation for us, but standard deviation cannot give directly the value of NPQ. So to get NPQ, we will take the variance. So variance is nothing but square of standard deviation. So accordingly, if you start applying this, you will get value of Q, which is 2 power 3. Once I know the Q, I can get the value of P, 1 by 3. So by substituting P here, I will get n is equal to 6. So sample is very, very small. P is given 1 by 3. Q is given 2 by 3. Now I can write the function. What is the function? Probability mass function is given by NCX, x power p, q power n of x. So this is the actual function that they are asking to calculate or identify. So 6cx, 6 is given, p is given, q is also given. So we can substitute in this for any x value, we will get the result. So this is what we have to calculate. So we should know this formula for mu, that is NP, formula for standard deviation, that is square root of variance, which is nothing but square root of NPQ. Okay. Now another problem, where x is binomially distributed, they have given 6 repetitions, they have given n, and p is also given. Then we have to calculate p, x is equal to 3, x is less than or equal to 3, x is equal to 4, p. So directly they have asked you, asked as probably we can calculate by applying the formula. So I will leave it to you. Please go through that. You should be able to understand, because this is a direct application of binomial distribution. Next, another problem. Probability that a man aged 60 at present will have up to 70 years. That means will live up to 70. Currently the person who is 60 will live 10 more years up to 70. The probability is 6.5. What is the probability that out of 10 men now aged at 60, at least 7 will live till 70 years of their age? Again, we have to identify which distribution it is. So for this, n should be small. What is n? N is only 10. So okay. What is the outcome trial? A person living, not living. So it is binomial. So thereby we can consider this as a binomial distribution. So n is equal to 2. Probability that a person survives till 70 is 0.65. Q, the person does not survive, is 0.35. Now the question is probability that at least 7 men will survive till 70 years of age. So that's what I was talking about. At least 7. That means x should be 7 or more than 7. So x is greater than or equal to 7. You can calculate either like this, or you can calculate either this. So depending on our problem, depending upon the time available, probably we can choose the best option. 7, 8, 9, 10. So very close to 10. So I can do 4 iterations. Thereby I will prefer to go with this. So probably we can also follow. The result is 0.5138. Now the number of telephone lines busy at an instant of time is a binomial variate. They have already given binomial, no headache for us, with probability 0.2. If at an instant 10 lines are chosen, number is 10, randomly, what is the probability that 5 lines are busy, at most 2 lines are busy, all lines are busy? Again, I leave this as an exercise for you. Please go through that. You will be able to understand direct application of a binomial theorem. So here at most means what? Second probability they are asking is at most 2 lines are busy. At most, maximum, at least, maximum. So at most means x is less than or equal to 2. At most means maximum is only 2. It can be 1, it can be 0. So be careful with the word at least. So far we have used at least. Now we are using at most. So whenever there is at least, it is greater than or equal to. Whenever there is at most, it is less than or equal to. Please understand that English, and accordingly we can put this value. So now couple of problems are there for you to solve as a homework. Try to do them. They're all very quite simple and in line with the whatever we have done so far. So probably with this we can conclude our binomial distribution, which is very important from exam point of view. So in next video I will discuss about the Poisson distribution. Thank you.